Hello and welcome to Learn Data. It's great to have you on this channel. In this continuation discussion on Bayesian theory, this was what we discussed in the previous video. Now let's dive in further on next topic. Now let's look at one feature and how we can use a decision rule to classify a sample to a particular class. So here we have uh, posterior probability. So we classify as W, the sample belongs to class W1 if the posterior probability for W1 given X is greater than the posterior probability of class W2 given X. Otherwise, we classify it as the class W2. Now, uh, we can use this information to find the error in that particular action we take to classify a sample to a particular class. On the right hand side, we have this plot where if we look at this magenta dot on top, when we classify that dot as it belongs to the class W1 as a for caret, using the posterior probability because it's higher probability for class W1 than W2. Therefore, we classify it as W1. But then at the same time, we do have this associated error that that particular sample could have been classified as W2. And so that is the error that we are talking about here. So right here we classify it as W1, then the error would be the probability, posterior probability that the data point or sample could have been classified as the class W2 given X. And so if we try to find the average probability on error, this is the equation for that. We integrate over all the probability of error given X and multiply it by the probability of X. And then finally, the equation that we have here is that which is the minimum of probability of class W1 given X, uh, or the probability of class W2. So whichever is the minimum. Now we have seen the decision rule using the posterior probability, which is given by this formula for Bayes, where we have this scaling factor or evidence in the denominator, the job of which is to uh, transform or convert, bring this particular scale, this uh, value from the numerator, which is the product of likelihood and prior, into a range 0 and 1. And so the probability, posterior probability, then what we get is a value that is between 0 and 1, and that is given by this particular formula. Now what if we drop that scaling factor and just use the value that we get from the product of the numerator? So that's also usable, and so we can use just the numerator to perform a decision. So if that value is higher for a class, say W1, we classify it as the sample belongs to class W1. Now, so far we have looked at just one feature vector. Now, if we have more than one feature vector, so we have multiple features, so in that case, we are now looking at a matrix, and so the notation has changed. So the change is that the X is now boldface X, and that is, and we can imagine it as a matrix. Let's say for each column represents a vector and each row represents a sample. So each column represents a feature and each row represents a sample. uh, so we have circularity, red channel, values, and then so on for the features. So if you are in the food processing plant, you could create, let's say, 50 features and collect maybe 100 samples. So you'll have like 100 by 50 matrix that would be input to the model. Now these are some terminologies that we are going to use. We already have seen omega 1, which is for the class. I think I was calling it as W. So the omega 1, and then we have actions, which is denoted by alpha. So action or decision function is the act of classifying a particular vegetable as either carrot or a turnip, or not classifying in either of those two classes because maybe it's an apple. So that's what action is. So it's the just the action of taking that step to classify something. And then the loss here is given by lambda, and that is based on alpha given the class omega j. Now the risk, using the loss that we have, we can calculate the risk. So if we multiply the value of loss with the posterior probability and add them up for all the classes, so in this case for vegetable example we have just two classes, carrot and turnip, so the value would be j equal to 1 to 2, c is equal to 2, and so that will give us the value for risk. So the idea then is to minimize the loss to reduce the risk. And so with that, we can calculate the overall risk by this integral as shown here. The teal color, what we have is we are trying to multiply the loss and posterior and then multiply it by the evidence which on the right hand side here. So we are not going through the derivations of these equations. If you are interested in the derivations, the book chapter does have those in detail. Here we are just going over steps within those to get an intuition of how and where those equations have come in and how those decision rules were created. Now, with that overall risk R, uh, when we find the minimum value of R, that is also denoted by R star, is called as a base risk. Now, for a classification problem of two classes, let's assume we have class omega 1 and omega 2, and then the action to classify as omega 1 would be alpha 1, and alpha 2 would be to classify action to classify a sample as omega 2. And the loss, we have a slight change in notation, writing this term on the right hand side. So what this means is that the loss incurred when we take an action to classify a sample as it belongs to class I, when the true class is j. So that's the what this lambda ij is trying to tell. Now using that information we can compute the risk for the risk as shown here for the action alpha 1 given x and alpha 2 given x. So in each of those cases, we are multiplying the posterior probability by the loss values. So lambda 1 1 tells us that we took an action to classify the sample as it belongs to class 1 when the true class is class 1. So that's a loss value for correct classification, and this is loss value for incorrect classification where the true class is 2 and the predicted class was 1. And so based on those values for risk, we can arrive at this decision route with minimum risk, which says that the classify sample as belong to class W1 if the risk value for that action taken given the data is less for that class as compared to other class. So in this case W2. We can also use posterior probability along with the loss. So here what we are trying to do is multiplying the posterior probability with the difference between the correct and incorrect prediction, correct or wrong prediction. So the lambda 2 1 would be the incorrect classification and lambda 1 1 would be the correct classification. When we take the difference of those, I like to think about this as weighing, adding weight to the posterior probability uh, to arrive at this decision rule. So if the product of this is higher, then we classify it as W1, else W2. Similar to this, we can also use the conditional probability, class conditional probability, likelihood multiplied by the prior, and again weighing it by the difference between the losses. And again, if this term for class omega 1 is uh, larger than the product here on the right hand side for omega 2 class, then we classify it as belongs to class 1. Moreover, we can also use likelihood ratios. So here we have the likelihood ratio on the left hand side. So likelihood for class 1 divided by class 2. And again, on the right hand side, what we have is the priors that are weighted by the loss difference. So we can have preset threshold, and based on that, we can say if the likelihood is greater than that threshold, then classify that data point or sample as that it belongs to class omega 1. And this is under the assumption here that is shown on the right hand side that the loss or the correct class is always less than the loss for the incorrect classification. What it says. Now, on this plot that we have seen before, we have the posterior probability curves, and the point where both of these curves intersect, that's the point where the probabilities for both the classes is the same. So it could be classified as carrot or it could be classified as turnip. So both have a posterior probability of 0.5, and the dotted line shows the decision boundary at that point. So this is arbitrary location. It could have been anywhere on this plot, but I've chosen to there. Now, if we pick a point, magenta dot shown here on the orange curve, we see that it has a higher posterior probability than the same dot if we plot it on the purple curve below it, and therefore we classify this sample as that it belongs to class omega 1, which is carrot and not a turnip. But when we do that classification, when we take that action to classify it as belongs to class 1, that is a carrot, we also have this information where we know that it could have been, it also has associated probability that it could have been classified as belonging to class omega 2. And so this particular probability, posterior probability that we have is used as error in setting up the decisions. That was it for this video. We'll continue this discussion in next video. Until then, please like, share and subscribe. I hope to see you in the next video as well. Thank you.